In this lecture, I will present a design of a beam for combined flexure, shear, and torsion per ACI 318. The beam is a cantilever 6 feet in length, subject to a dead load of 2 kip per foot and a live load of 3 kip per foot. We go and proceed to compute the two corresponding load combinations for this situation, which is 1.4 dead, and that results in 2.8 kip per foot, and 1.2 dead plus 1.6 live, which results in 7.2 kip per foot. And that is our controlling load combination because it results in the highest load per linear foot. The cross section of the beam is shown here on the right. It's an L beam. The load is applied at the center of the 12-inch bracket and therefore results in an eccentricity of 16 inches. The eccentricity is nothing more than the distance between the load and the center of the beam. In this case, for simplicity, we will assume the centroid of the beam is 10 inches from the edge, and then 10 plus 6 results in the 16-inch eccentricity. From the value of the ultimate load, the length of the beam, and the eccentricity, we can compute the ultimate values for the design shear, moment, and torsion, as shown right here. So for the shear, we basically have load times the length. For moment, we have load times length squared divided by 2. These are basic results from statics, strength of materials, structural analysis. And then the torsion we obtain by multiplying the total shear by the eccentricity, which, as we have already mentioned, is 16 inches. So we obtain ultimate shear of 43.2 kips, ultimate bending moment 129.6 kip feet, and ultimate shear 57.6 kip feet. Now we are going to design for each individual effect. For bending, the first thing we do is check the minimum steel, and in this case, with a D of 27 as a preliminary value, since we haven't decided on the longitudinal reinforcement yet, but that's going to be conservative because we have a clear cover of 2 inches. So 30 minus 2, 28, and then we subtract 1 more inch to get to 27. If we use B of 20 inches, D of 27 into the ACI formulas for minimum steel, which are right here, we obtain a minimum longitudinal reinforcement of 1.9 inches square. That is going to be 2 number 9s, which result in 2 inches square. So we're going to use 2 number 9s as longitudinal reinforcement, and now we're going to proceed to compute the moment capacity provided by the 2 number 9s right here. Right? So first we notice that the compression zone is in the wider width of the beam, and so when we compute ASFY divided by 0.85 BF prime C, the B value is going to be 32 inches. The yield stress for steel is 60 KSI, AS is 2 inches square, F prime C is 4 KSI, if you do the calculations, that results in 1.10 inches. That is the depth of the effective compression block. With that value of A, we can go into the formula for moment capacity, which is AS/Fy times D minus A over 2. Now that we have selected our reinforcement as two number 9s, we can compute a more precise value of D, as shown right here. D would be 30 minus 2 plus 9/8 divided by 2. 9/8 is the diameter of a number 9. That results in a D of 27.4, and if we substitute into the formula with all the corresponding values, we obtain a nominal moment capacity of 273 kip feet. With a phi of 0.9, we obtain phi mn equals to 246 kip feet, which is greater than the 129.6 kip feet from the demand, and that means that our design is adequate and there is no need to add more than the minimum reinforcement, which is 2 number 9s.